Second half of the midterm review. We have an object on an inclined plane, 5 kilogram mass, 2 strings, 30-degree incline, vertical string, 6 newtons, ramp is frictionless. Alright, so first thing we want to do is draw our force diagram here. 5 kilograms, right, so that's got a force of gravity going straight down. It's got this little force of tension going up here. FT we're calling it. I guess I'll call it just FT. Maybe I'll call it FT1. Then along the incline here, so along the incline we have another force of tension, FT2 I suppose I'll call it. And then perpendicular to the incline we're going to have Fn. Now my coordinate system here, I'm going to draw it so everything's parallel to the incline here and perpendicular to the incline. So this angle is 30 degrees. Have to know that. Now any other forces, we got the 2 ropes accounted for, we've got gravity accounted for, and normal force, there's no friction. This looks good. Now the 30 degrees is going to come into play up here as well. It's going to be this angle. It's going to be 30 degrees. We're going to have to break that FT1 into 2 components. Okay, so it says determine the normal force acting on the block and the force of tension that the string parallel to the plane applies. Include a force diagram. So let's go ahead and look at X and Y direction. It starts off just a regular old statics problem, right? So even if it wasn't a statics problem, we would want to break these forces into their X and Y components. So FT1 X, alright, that's going to be here, length that side, or it's going to be parallel to the plane down here, really, right, that way. FT1Y is going to be that way. FGX is going to be this way. FGY is going to be down that way. FGX is going to be that way. So FT1X is 6 times the sine of 30. FT1Y is going to be 6 times the cos of 30. Y is going to be the adjacent side. FGX is going to be, alright, so this is 5 kilograms, so it's 50 times the sine of 30. FGY is 50 times the cos of 30. Alright, I could find all these numbers if I wanted to. I will eventually here, so I guess I can go ahead and just do that now. Alright, so 6 times the sine of 30 will be 3 newtons. 5 times the sine of 30, 50 times the sine of 30 will be 25 newtons. 6 times the cos of 30 is 5.2. 50 times the cos of 30 is 43. Alright, now there are going to be signs on these, negative and positive, but we can put those on once we do Newton's second law. So, in the X direction, which way do I want to make positive, which way do I want to make negative? I guess I'll make down the ramp positive here and perpendicular ramp positive. Doesn't matter as long as we're consistent. So in the X direction, if I'm doing positive, I'm going to have FGX positive, and then I'm going to have minus FT2 minus FT1X equals 0. All right, we've got 2 forces parallel to the x-axis. We have literally just the straight up FT2. Then we have the x component of FT1. Right, FT1's part of it is pulling it up the ramp. In the y direction, we're going to have Fn plus FT1y in the positive direction minus FGY. equals 0. So they all have to add up to 0. We have 2 positive forces, 1 negative force. We have, sorry, 2 positive forces, 1 negative force. Here we have 2 negative forces, 1 positive force. So let's go ahead and put some numbers in and see what we can do. So FGX, we said, is 25 newtons. FT2 is unknown. FT1 X component is 3 newtons. Alright, so that tells us FT2 must be, bring the 25, negative 25 newtons plus 3 newtons. FT2 must be negative 22 newtons. So FT2 is doing a lot of work to hold up that block. FT1's Y component, or X component, is fairly insignificant. Alright. Let's go over here to the Y direction. Fn is unknown, so we're just going to leave that Fn. Ft1Y is 5.2 newtons. Fgy is 43 newtons, so it's minus Fgy equals 0, so Fn equals 543 minus 5.2, about 37.8 or 38 newtons, and it comes out positive here. So that wasn't too bad, you know, statics problem. We just got to make sure we really know what we're doing with the inclined plane. Now, if the string is cut, what is the acceleration of the block down the incline? Alright, so if the string is cut and it's frictionless, alright, what forces are acting? We just have Fg and Fn. So I'm going to draw a separate force diagram down here. Alright. So we're looking for basically just the x direction. F net x equals max. What we're looking for is max. So the net force in the x direction, the only thing there is fgx. That's all there is. There's no friction, so I don't have to worry about it. So F net x is just fgx equals max. Fgx, we already calculated. Beautiful. 25 newtons equals, and that's why it's worthwhile sometimes to do these on the side, because if you just did it right in the equation, you know, you'd probably have to do it again here. But since we already did it up here once, now down here I can just throw in what I got up there. So 25 newtons is the force pulling it down the ramp. Its mass is 5 kilograms. AX is what we're looking for, so divide by 5, divide by 5. A equals 5 meters per second squared down the ramp. Alright, not too bad. I like that one. It starts off static, but then turns into a fairly simple dynamic problem. Alright, next one here. Final one of this packet. It's a fire airplane dropping some water. The illustration doesn't really do us much favor because it's a weird 3D perspective, but the angle it's flying at, I suppose, is like 15 degrees, so maybe you can try to visualize that. I'll draw it again down here though. So got some, you know, airplane dropping water, right? The water, believe it or not, pretend it's like just like a big blob of water. It's actually going to move forward with the same initial speed as the plane. All right, so its initial speed forward is 60 meters per second. And its height is 300 meters. That's going to fall. Delta Y is going to be actually negative 300 meters, I suppose. Alright, so the blob of water is actually going to fly through the air and eventually hit the ground down there somewhere. You know, this shows a stream of water, but That's fine. Oh, my illustration here is lacking, right? Because this whole thing's supposed to be flying up. That's my bad. Right, so it's actually going to go up. Oh man, my illustration failed miserably here. So, gonna have to edit this, I suppose. Ignore those blobs. I forgot about that. So it's gonna go up and then come down. So its trajectory is gonna look something more like that. All right. So first thing we want to do here is break that into x and y components, that initial velocity. V naught x equals 60 meters per second times the cos of 15 degrees. V naught y is 60 meters per second times the sine of 15 degrees. All right. So 60 times the cos of 15, is about 58 meters per second. So small angle approximation here almost. 60 times the sine of 15 degrees is about 16 meters per second. So it's launched up at 16 meters per second, horizontally at 58 meters per second. Now it's just a matter of plugging into the x and y direction. AX is 0, AY is negative 9.8 meters per second squared. So I'm going to make down the negative direction here. So, x direction, we've got delta x equals 1/2 AX t squared plus V naught xt. That term is just 0. All right, so delta x is how far forward it's going to move while it's falling. So we want to make sure we release the water that far in front of our drop zone, right? Because that's how far forward it's going to move. So delta x is the unknown quantity. V naught x is 58 meters per second. T, we don't know yet. So let's go over to the y direction. All right, y direction. We've got delta y equals 1/2 AY t squared plus V naught YT. All right, so we've got negative 300 meters equals 1/2 of negative 9.8 meters per second squared times t squared plus 16 meters per second times t. And what we have here, unfortunately, is a quadratic. 4.9 t squared plus 16t plus 300. I just use my calculator to get the roots, right? I gotta remember how to do it on this one. Where is it? Is this it? Yeah, there it is. A equals negative 4.9. B equals 16. C equals 300. Solve it. I've got two roots here. I've got negative 6.36 and 9.6. So it tells me the positive root is 9.6. That's the one I'm going to take. 9.6 seconds. Sounds about right. I could go back and plug it in here if I was really worried about it being the right root, 0.5, right? 0.5 times negative 9.8 times 9.6 squared plus 16 times yep, negative 300 is about what I get there, so that's good. All right, so now I can take that time I had plug it back in there. Delta x equals 58 times 9.6. It's going to be about 600 or so, a little under 550, I suppose, maybe. About 557, 560, I'll say. 560 meters it's going to travel forward. So, you know, must released. $560 meters before the fire. All right. Used calc. Used calculator to find roots. That's totally fair game. You have your calculator. You can always do that. That's not a problem. All right, so that's the end of that video. The front notes here. I don't know. I think you should probably try writing these up, but I can do a bit for you here. And I'll post that later.